This is section 16.7 on surface integrals. We'll be integrating across surfaces now. On page 1122, surface integrals. Right, so imagine we're integrating along a surface. Something that looks like this, or like this. Okay. And this is in general a surface in space. We already know how to handle something in the XY plane, but maybe we're integrating across something like this. All right, so there are several versions of this. So formula 2 is a good one. Integral, double integral of a region S of f of x, y, z ds is double integral along the region D. Now D is in the XY plane. S is a surface in space. If you project down to the XY plane, you have f of r of uv times the magnitude of ru cross rv dA. Okay, so that's one possible formula that we have. Okay, and then where z is a function of x and y, page 1125. Okay, number 4, integral, double integral along the surface of f of x, y, z ds is double integral over d. Again, S is a surface in space. D is back in the XY plane, as long as the z is a function of x and y. So f of x, y, g of x, y, which means change z to something involving x and y. And then the formula for ds that we had in the last section, square root of partial with respect to x squared plus partial with respect to y squared plus 1 dA. Now, last section we were doing surface area, where all you had was this part. Okay, but now we're doing a surface integral, so you're integrating some function. And then on top of that, ds, which is all this stuff here. Okay, so we might have that. Okay, what they're trying to show you over here is you could have y as a function of x and z, then equivalently, you change to h of x as z and square root of y sub x squared plus y sub z squared plus 1 dA. And likewise, you could have x as a function of y and z. Okay. All right, then we have oriented surfaces at page 1127. Okay, so in general, positive for z as a function of x and y, positive is considered up. Okay, so you see these normal vectors are going up, that would be positive orientation. The vectors going down would be negative orientation. So that's if you have z as a function of x and y. And equivalently, if you have y as a function of x and z, then y positive would be facing to the right and negative would be to the left. And if you have x as a function of y and z, then positive would be out because that's the way the positive x direction is and negative would be in. But most of the time we'll have z as a function of x and y, in which case positive would be up and negative would be down, as we are aware of. Okay. To get a unit normal vector, we have this. Okay, if you want to go at g, g is the same as z. You could have just said negative z sub x I minus z sub y j plus k over the square root of that thing squared plus that thing squared plus that thing squared. Okay, so we have that. We also have this form for unit normal vector, or u cross rv divided by its magnitude. For a closed surface, page 1128, by convention, if you have a closed surface, like a sphere or a box or some closed surface, positive orientation is considered out, negative orientation is considered in. That kind of makes sense because if you're going out, you can go infinitely far out, so we like that to be positive, but normally there's a limited amount of space you can go in, and therefore you don't have negatives going to infinity. If you reversed it, you can say going outward is negative, well, you might have negative 1,000,000, negative 1,000,000,000, negative 1,000,000,000, and only a little bit positive. And we said, okay, we like the fact that these can go as big as possible. We want this to be a positive number to go out to 1,000, 1,000,000, 1,000,000,000, and only a small, quote unquote, number, bounded number for negatives like negative 10 or negative 20 or something like that. Okay, then surface integrals of vector fields. So quite often, again, you're integrating across a surface. So this could be interpreted as flux of F across S, page 1129, surface integral, double integral of F dot ds. So one form is double integral of F dot n ds. Okay, notice that's a vector and that's a scalar. D vector S is the same thing as unit normal vector times ds, and this is a scalar. This can be interpreted as the flux of F across S. Okay, so if you have some surface, okay, the flux across a surface, it could be water, it could be electricity, it could be anything that you want to measure, a fluid, the amount of fluid flowing across a surface. It could be heat, temperature that you're studying. Okay, and then if you don't have z as a function of x and y, but something more complicated, written parametrically, then you want to use number 9, double integral across s of f dot ds, double integral of f dot ru cross rv dA is another form of the same thing. Okay, so you can see here, figure 11 shows a vector field F, as you're saying, at points on the unit sphere. Okay, so it looks like sometimes perhaps this can be heat going out, heat going in, electrons coming in, electrons going out, water going in, water going out, or whatever you have to be studying. Okay. All right, then page 1130. Another version for double integral of F dot ds, flux of F across S, is negative P partial of G with respect to X, and don't worry about G, it's the same thing as Z. You could have said the partial of Z with respect to X, minus Q partial of Z or G with respect to Y, plus R dA. Okay, and again, dA, you're back in 2 dimensions. Normally dx dy or dy dx would be the case there. Okay, now some of these problems can get really long. So if you look at the homework assignment, I cut out any that I thought would be super long, namely 13, 17, 19, 21. They're good problems, but they just take too long to do. So that's the reason why I decided to shorten the assignment a little bit. All right, so I think we're ready. 16.7. Had to go as high as what? Problem number 31. 1. Whoops. Accidentally hit the. Okay, 3, 5. Okay, 7, 9, 11, 13, 15, 17, 19. Oops, maybe 21. 23, 25, 27, 29. I think 29 was the last one we had to do. All right. All right, number 1, you have this box, negative 1, 1 cross negative 1, 1 cross negative 1, 1. Okay, dA for any of the 6 surfaces is 2 times 2, which is 4. 2 this way, they're all the same. Okay, and then they ask us to use the midpoint of each. Wording of it. Use a Riemann sum, and the points to be the centers of the squares. So the centers, front is 1, 0, 0, back is negative 1, 0, 0. Left is 0, negative 1, 0. Right is 0, 1, 0. Top is 0, 0, 1. Bottom is 0, 0, negative 1. And we're guesstimating the double integral of cosine x plus 2y plus 3z ds. All right? So dA for each of these is going to be 4. They're all 2 by 2. So I factor out the 4. And then I have cosine of, well, the formula goes x plus 2y plus 3z. So cosine of 1 plus 0 plus 0, plus cosine negative 1 plus 0 plus 0, plus cosine 0 plus 2 plus 0, plus cosine of 0 plus negative 2 plus 0, plus cosine of 0 plus 0 plus 3 plus cosine of 0 plus 0 plus negative 3. Okay, and cosine of 1 and cosine of negative 1 are the same. Cosine's an even function. Likewise, cosine of 2 and negative 2 are the same, and 3 and negative 3. So I got 4 times 2 cosine 1 plus 2 cosine 2 plus 2 cosine 3, which is 8 times cosine 1 plus cosine 2 plus cosine 3, which is approximately negative 6.93. All right, 5. You want the double integral over the region S of x plus y plus z ds. Okay, and they give you these parametric equations. X is u plus v, y is u minus v, z is 1 plus 2u plus v. U is going from 0 to 2, v is going from 0 to 1. So figure out x plus y plus z. So x is u plus v, y is u minus v, and z is all that, which comes out to be 4u plus v plus 1. Differentiate with respect to u. That's easy. 1, 1, 2. Differentiate with respect to v. 1, negative 1, 1. And then I need the cross product. Ru cross Rv, ijk, 1, 1, 2, 1, negative 1, 1. The I component is 1 minus a minus 2, which is 3. The j component is the opposite of 1 minus 2, negative of negative 1. And the k component is negative 1 minus 1 or negative 2. So this is the vector 3, 1, negative 2, whose magnitude is the square root of 3 squared plus 1 squared plus 2 squared, radical 14. All right, so the integral is double integral from u equals 0 to 2, v equals 0 to 1, 4u plus v plus 1 times radical 14 Jacobian dv du. Take out the radical 14 and integrate with respect to v. So 4uv plus v squared over 2 plus v. Plug in 0, you get 0. Plug in 1, you have 4u plus a half plus 1. That's 3 halves. And I integrate with respect to u. So that's 2u squared plus 3 halves u. From 0 to 2, plug in 0, you get 0. Plug in 2, you get radical 14 times 8 plus 3, 11 radical 14. 7, double integral over the region S of y ds. And R is given this definition. So u cosine v, u sine v, v, u going from 0 to 1, v going from 0 to pi. All right, differentiate with respect to u, cosine v, sine v, 0. Differentiate with respect to v, negative u sine v, u cosine v, and 1. Cross product. ijk, components of ru, components of rv. So I component is sine v minus nothing. J component is the opposite of cosine v minus nothing. And the k component is u cosine squared minus a minus u sine squared. And of course, you factor out the u, you get cosine squared plus sine squared v, which is 1. So that's u. Okay, what is the magnitude of the cross product? So square root of sine squared v plus cosine squared v plus u squared, or 1 plus u squared radical. So I is the integral 0 to 1, 0 to pi of y. Y was u sine v times the Jacobian radical 1 plus u squared, magnitude of ru cross rv, dv du. All right, and let's see, this thing does not depend on, oh, I take that back, never mind about that. I integrate with respect to v first, integral of sine and negative cosine from 0 to pi. So I have the opposite of negative 1 minus 1, that's 2. Okay, and let's see, if I do a u substitution, well, a v substitution, the derivative of 1 plus u squared is 2, so I'll put the 2 back in, and it's perfect. So this is 1 plus u squared to the half, therefore 1 plus u squared to the 3 halves times 2/3 from 0 to 1. Plug in 1, I get 2/3 is outside, 2 to 3 halves, plug in 0, you have 1. So 2/3 of 2 radical 2 minus 1 is my answer. Okay. 13, double integral of z squared ds. X is y squared plus z squared. X goes from 0 to 1. So that means 1 equals y squared plus z squared in the extreme. Okay, so x, the function of y and z. X of y is 2y, x of z is 2z. So I have z squared, which is r squared sine squared theta, that's z squared, radical 1 plus x of y squared, x of z squared, which comes out to be 1 plus 4r squared sine squared theta, r d theta, switch to polar coordinates, and theta is going from 0 to 1. R is going from 0 to 1, theta is going from 0 to 2 pi. This turns out to be quite long, so I just had to skip it. I just do the intro to that one. Okay. And then 15, y is a function of x and z. X and z are both going from 0 to 1. So again, you don't have to have z as a function of x and y. You can have x as a function of y and z, or in this case, y is a function of x and z. Okay, so y sub x, 2x, y sub z is 4. Integral from 0 to 1 of x, radical 1 plus 2x squared, 4x squared, and 4 squared, 16, which gives me 4x squared plus 17, whose derivative is 8x. Put an 8 here, 1/8 out there. Okay, and this integral does not depend on z, so take out the length of the z integral, which is 1, which means don't do anything. Okay, the derivative is 8x, put 8 here, 1/8 there. So 1/8, 2/3 of 4x squared plus 17 to the 3/2. That comes to be 1/12. Plug in 1, 21 to the 3/2. Plug in 0, 17 to the 3/2. Final answer, 1/12, 21 radical 21 minus 17 radical 17. Okay, give you the setup for 17, but we're skipping it. I'll just show you that it comes out to be long. Factor out the z. You've got a sphere here, which can be written as rho 2 sine phi cosine theta. Y is 2 sine phi sine theta. Z equals 2 cosine phi. But it turns out to be quite messy, very long. So just give you a feeling of what it looks like. So I decided to skip it because it came out to be much too long. And that was 17. Okay, 23. F of x, y, z, p, q, and r. Z is 4 minus x squared minus y squared. X and y both going from 0 to 1. Oriented upward, so that's positive. Okay, so I'm using the formula double integral of f dot ds is negative p partial z with respect to x minus q partial z with respect to y plus r dA. So first, negative p, so that's negative xy, then the partial of z with respect to x is negative 2x, and then minus q, so minus yz, partial of z with respect to y is negative 2y, plus r. So r is zx, but z is all that. Zx dA. So that's what I'm trying to integrate. So this comes out to be 2xy squared. This comes to be 2y squared z, and here's z again, plus all of that. So it's messy, but it comes out. Some messy algebra. 2x squared y plus 8y squared minus 2x squared y squared minus 2y to the 4th. And then I distribute the x and I get all that. And now I integrate with respect to x. 2x cubed over 3y, 8xy squared minus 2/3 x cubed y squared minus 2xy to the 4th plus 2x squared minus x to the 4th over 4 minus x squared over 2y squared. Plug in 0, you get 0. Plug in 1, 2/3 y plus 8y squared minus 2/3 y squared minus 2y to the 4th plus 2 minus 1/4 minus a half y squared from 0 to 1. All right, so 2/3 y squared over 2, 8y cubed over 3 minus 2/3 y cubed over 3 minus 2y to the 5th over 5 plus 2y minus 1/4 y minus 1/2 y cubed over 3. Plug in 0, you get 0. Plug in 1, you get 1/3 plus 8/3 minus 2/9 minus 2/5 plus 2 minus 1/4 minus 1/6. Heavy duty arithmetic, 713 over 180. Okay, 25. F of x, y, z is that. The surface is x squared plus y squared plus z squared equals 1, which parametrically, I use my formula for spherical coordinates, except rho is 1. So x is sine phi cosine theta, y is sine phi sine theta, z is cosine phi. Okay. It does come out to be fairly long. Okay. But I think I can actually work this one out. So yeah, I worked this one out. So F is X, there it is, Y, there it is, and Z squared, there it is. All right, so I did R sub phi, differentiate with respect to phi. So let's see, cosine phi, cosine theta, cosine phi, sine theta, and negative sine phi. Then R sub theta, differentiate with respect to theta, negative sine phi, sine theta, sine phi, cosine theta, and 0. Take the cross product. So nothing minus a minus or positive, sine squared phi, cosine theta. Okay, then the opposite of nothing minus a minus a minus. Okay, so it turns out to be a quadruple negative, sine squared phi, sine theta. And then the k component is that minus that. You can work it all out, but it comes out to be sine phi, cosine phi, because there's some cancellation involved here. See, there's a cosine squared, there's a sine squared, right? So you just combine all of these. All right, so you have that. All right, and F is X, Y, Z squared. We already had that. So I take the dot product, F dot the cross product. Okay, so it's going to be this dotted with this. So that times that, plus that times that, plus that times that. So we've got all this stuff here. So that times that is that times that is that times that is that. And put it all together, sine cube of phi, this is 1 here, plus sine phi cosine cube. All right, and this does not depend on theta, so take out the 2 theta. Okay, remember for spherical coordinates, if you got the entire sphere, theta goes from 0 to 2 pi, but phi only needs to go from 0 to pi. You don't have to come back around this way. All right, and you might recall how to do these integrals in Calc 2. Sine cube, make it 1 minus cosine squared times sine phi. And this one you can do a u substitution. Okay, so in any event, this comes out to be this, 1 minus u squared plus u cubed du. And let's see, distribute the negative 1. U cubed minus u squared plus 1. So u to the 4th over 4 minus u cubed over 3 plus u, negative 1 to 1. Plug it all in. 8/3 times 2 pi, or 16 pi over 3. Okay. And finally, 29, the flux of F across S. We give the definition of F. S is the cube with vertices plus or minus 1, plus or minus 1, plus or minus 1. So it looks like this. So we have 6 surfaces to consider: front, back, left, right, top, and bottom. Okay. So here's the one where it's recommended to do F dot N ds. I am doing this formula over here, because it's pretty easy to have the unit normal vector in a positive x direction. Okay, so F dot N ds. So the front is x equals 1. The unit normal vector going outward is I. So F dot N is x, 2y, 3z dot 1, 0, 0, comes out to be x, which is 1. And by the way, ds for all of these is 4. They're all 2 by 2. Back. The back, x is negative 1. So F dot N is negative x plus nothing, which is negative x. Which is going to be 1 again, because it's negative of negative 1. All right, the left, the unit normal vector is negative j, which is 0, negative 1, 0. So the dot product is nothing. Minus 2y plus nothing. So it's negative 2y, but y is negative 1 or 2. Right side, unit normal vector is j. F dot n is x2, y3z dot 0, 1, 0, which is 2y, but y is 1, so you just get 2. Top unit normal vector outward is k, 0, 0, 1. So F dot n is nothing plus 1, which is 3z, but z is 1, 3. And for the bottom, the unit normal vector is negative k, which is 0, 0, negative 1. So the F dot 0, 0, negative 1 is nothing plus nothing times negative 3z, but z is negative 1, so negative 3 times negative 1 is 3. Add them all up. So F dot ds is 4 times 1 plus 1 plus 2 plus 2 plus 3 plus 3. And so the final answer comes out to be 48. All right, so that's section 16.7.